Hello everyone. This is Mrs. Padmashri from SNS College of Engineering. Today I am going to explain the concept of VGG network, which comes under convolutional neural network architecture. As we discussed earlier about the several architectures of convolutional neural network. The first one we have discussed about the AlexNet architecture. The second one is VGG architecture. See the layers of VGG architecture. So we have the layers of VGG here. You have the input and the next will be the output. So between these input and output, we have the layers of convolution layer 1 to 1, convolution layer 2, polling layer, convolution layer 2, convolution layer 2 to 2, polling layer, convolution 3, convolution layer 3, polling, then convolution layer 4, 5, and the last will be the dense layer. So this is the architecture of VGG 16 version. So I'll be explaining about the layers of VGG. The here breakdown of VGG 16 architecture based on the provider detail. It has the input layer. The input dimension layer dimension is 224 into 224 into 3 convolution layer. So we all know the operation of the convolution layer is just it has the filter and it just filters the unwanted data in the layer, and also it provides the process of scanning the pixel data images of the data. So convolution layer has 64 filters, 3 into 3 filters with same padding. We have a two consecutive convolutional layers with 64 filter, and the filter size is 3 into 3. Same padding is applied in order to maintain the spatial dimension. Next layer is a max pooling layer 2 into 2 with two strides. So the max pooling layer with a pool size 2 into 2 and strides of 2. The convolutional layer 128 filters. We have 3 convolution layer, right? So the second one has 128 filters 3 into 3. Two consecutive convolution layer with 128 filter. Max pooling. As we have already discussed about the structure of and the operation of max pooling network in AlexNet architecture, right? So the max pooling layer with the pool size 2 into 2 with the strides 2. So convolution layer, uh, there are three, four convolution layers we saw, right? So the next will be two consecutive layer with 256 filter. The other one is 512 filters with 3 into 3 filter size. So the max pooling layer, it has 2 into 2 size, and it has a stride of 2. Max pooling layer with a pool size 2 into 2. Then there will be a stack of convolution layer. See, as we have just discussed in this diagram, see, we have convolution layer 1, 2, 2, 1, 3, 4, 5. There is a stack of convolution layer here, right? So the stack of layer, two additional convolution layer after the previous stack. The sizes, filter size 3 into 3. Flattening the output feature, which maps 7 into 7 into 512 into the vector size 25088. So this is all about the VGG 16 architecture and the layers, what all the important layers present in the architecture. As we have already discussed about um, convolution layer, just to process the pixel data, and we have the filters in it to filter the unwanted the data present in the layer, and we have the pooling. So the concept of pooling we already discussed in the previous architecture. It keeps off all the necessary feature, and it removes the unwanted error or noise from the network. Is the main operation of the pooling layer, max pooling, as we discussed, right? And the filters will be there. Then we have discussed about the layers of AlexNet. Almost the architecture is same. Almost the architecture is same. So the next is softmax. Softmax is typically used in the last layer. Like how in AlexNet we have the last is fully connected layer, fully connected layers. So here we have a softmax is used the last layer of the neural network to predict the class of the input image. Okay, and it is also used in other application, NLP, natural language processing, and also machine translation. ReLU, I hope you all remember, rectified linear unit. This we have discussed in AlexNet architecture as well. Here also we are having the same ReLU unit. So the purpose of having this unit, um, ReLU, do you remember? Like why we have this to overcome the drawback of overfitting. Overfitting, we are using this ReLU, and also to many things we have discussed, right? So the ReLU is typically used in the hidden layer of neural network in order to add the non-linearity. Okay, so these are all the thing. The VGG16 has fully connected layer, as we already, as I discussed, it's three fully connected layer with ReLU activation. First layer of input size 25088, output size is 4096. Second layer with input side 4096, output will be 4096. Third layer, because why we have this, see, you can see here the output of the first layer will be given as an input to the second, and the output of the second will be given as an input to, because it's a feedback and feed forward network. Neural network is a feed forward network, right? So the processing will takes place uh, one by one. So from the convolution layer 1 to 2, 2 to 3, 3 to 4, it goes on. So the third layer input size is 4096 and output is 1000, corresponding to 1000 classes. So the softmax is applied to the it's the last layer. It is applied to the output of third fully connected layer for classification. So then this architecture, this model 92.7 achieves the accuracy, test accuracy on the ImageNet dataset, which contains 40 million images, belongs to 1000 classes. So we can able to give 1000 classification, and which can able to detect, uh, contain the dataset of 14 million images. So the main VGG16 objective is the ImageNet dataset contains the images of fixed size of 224 into 224 and have RGB channels. So we have a tensor of 224, 24 to 24 into 3 as our input. So this model process the input image and output, process the input image and outputs the vector of 1000 values. So this is considered as a very good advantage of this model. And this model to have some limitation, very slow to train because it has a very large data set. So it can able to do 1000 classification. So obviously the network will be slow. So the original VGG model trained with the name NVIDIA Titan GPU for 2 to 3 weeks. Size of this VGG16 network is 528 MB. So it takes a quite lot of disk space. It occupies more space. So the bandwidth what we get will be inefficient. So there will be a 138 million parameters lead to exploiting the gradient problem. Then further advancement, resonance are introduced to prevent exploiting gradient problem that occurs in VGG16. So this is all about VGG16. It has some drawback. You have to remember this. Then I'll be discussing in the next architecture ResNet. So we are going to overcome the problem of VGG. What is that? Exploiting gradient problem. This problem will be overcome in in ResNet. So the rest we will discuss in the next lecture series. Thank you.